Hello and welcome to another video. In this video, we're going to be working on a 132 pattern. So in this problem, you're given an array of nums, and a 132 pattern is a subsequence of three integers, nums I, nums j, and k, such that I is less than j is less than k index-wise, and the nums I is less than nums k is less than nums j. Return true if there is a 132, and false otherwise. So in this first example, there isn't, but let's take a look at some of the other ones. So we have 3, 1, 4, 2. And in this one, there is a 132 pattern because if this is I, this is j, this is k, that works, right? J is greater than I, k is less than j, but is still greater than I. And then in the second example, there is also a 132 pattern, and there's a bunch of them, but this is like one of them. So if this is I, this is j, this is k, that also works, right? I is less than j, I is less than k, and k is less than j. So the brute force, obviously, is to just go through every combination of I, j, k, and that would be n cubed. But what we're actually going to try to do is we're going to try to find a good way of storing I and j, and then we are going to be using those to be getting k. Or we're gonna try k from those stored I and j. So let's actually look at some problems. Like, let's say we do have this, like, maybe 3, 1, 4, 8, 9, 2, let's say we have something like this. So how do we find an efficient way to store I and j, pretty much? And let's just think about one thing first. So let's just say we have some j value. Like, let's say this is our j. What would be the best I for that j, right? The best possible I. Well, the best I for any j is always just going to be the smallest number in the array before it, right? So for like this j, the best I is this. For this j, the best I is 1 as well, right? So for every number past 1, the best I is going to be 1. So to store I is going to be pretty straightforward. We're just going to store the smallest number we've seen so far, and that's obviously going to be like the best I. Now, to store j, it's going to be kind of tricky, and we need to store multiple values, and I'll kind of show you why. But essentially, what we're going to be doing is we're going to be storing a combination of j and I, and then we're going to figure out like what j values are redundant. So for example, let's say we have this j value that we store, right? And this would be the I. And so this would be, like 8, 1. But what if we get to this j value instead? If we have this j value, like it's farther down. So also notice that as you go farther down, your I value is only going to get better and better, right? So if you think about it, like for the I values, like let's just say for all of these j values, what would be the I value? Let's try to figure that out, right? So for this value, there's obviously nothing because this can't be a j value, but let's say for this j value, this can't be a j value either because the smallest value we've seen so far is 3. But here, the smallest I we've seen so far is 3, so 3 would be here. Actually, no, sorry, it wouldn't be 3, it would be 1, right? So it would be 1, 1, 1, 1, but it can't get worse because it's the smallest value we've seen so far. So as we traverse right, our I value can only be the same or better. So knowing that, as we traverse right, our smallest value can only be the same or better, let's compare these two j values. Like if we have this j value stored with this I, so we have 1, 8 stored. If we get to 1, 9, do we even care about this 1, 8? Like, is there a k value that this would fail for and this would work for? Well, not really, right? We're maximizing our j value, which is good, right? We want to have the biggest possible j value possible. So if our I value remains the same, ideally we would want to have something like 1 or whatever I value we have, and ideally for our j we have like infinity because that maximizes the range k can be in, right? K can be anywhere from infinity to I now. So if you have 8 or 9, the biggest one is always going to be better. So when you have two j values and one j value is further down, any j value that's smaller is going to be useless pretty much, right? Because remember, our I value gets better and better and better as you go down. But our j value, we want to store the biggest one possible. So we're never going to want to store a j value that's smaller than one we're on. So if we have a bunch of j values and we get to bigger j values, we can just pop. Like we're going to be using a stack, we're going to pop j values that are redundant. And redundant j values are j values smaller than our current one because, like I said, our I is going to be optimized. So as you go down this array, I is optimized. I is going to be better and better and better and better. And then for j to be optimized, you want to have the biggest one possible. But you got to keep in mind, if j is decreasing, then you can possibly have something better. Like, you have to store both of those. So let's say we have a j value of, like, I don't know. Let's say it's like 100 here. We can't just be like this 100 is better than something down the road. We have to store actually both because, for example, let's say we have something like this. We have 30, 100, and now we have a smaller j value. So actually, we literally have, like, let's say, right, something like this. So we can't just store only 100, or else we're never going to have a solution here. The solution is actually 198 here. So as you go down the road, the smaller value can get a lot better, right? The smaller value is going to be here, the I value. So we might have to store smaller j values, but we're never going to store so our j values can be decreasing. So we can have like 100 and then 9 and then 8 and so on. But we're never going to store, if we have a 9 here and we hit like a 15 later, then we don't need this 9. This is redundant because the I value is only going to be better here or equal to here. So we're never going to want to use this value. So now that we know that our I values are going to be better or equal going right, and if we hit a j value that's bigger than previous j values, we can get rid of those, but not necessarily smaller, right? So our j values are going to be strictly decreasing, and then our I values are going to be equal or decreasing as well. So let's kind of walk through now what would happen here essentially and kind of how we do this. So we're going to start by keeping just some I value, whatever, like we're just going to make it infinity. And this I value is just going to represent like the smallest number we've seen so far. So we're going to come over here and we're going to have a stack, and our stack is going to have an I and a j value. So let's maybe just draw our stack like this just to have some variables. Something like this. Doesn't look great, but something like this. So our stack is going to have an I value and a j value. And we're only going to put things into the stack where the j value is greater than the I value. So for this number, obviously we can't put an I and a j because there's only one value, but we are going to update our I to be the smallest value we've seen so far. So the smallest value we've seen so far now is 3. I don't know what that is. Okay. Now we're going to come over here and we're going to say, okay, so the smallest value we've seen, first of all, our stack is empty so far, right? As you can see. So we can't like pop anything. And the smallest value we've seen is 3. So if this was a j value, we can't have 3, 1, right? J has to be greater than I. So we can't really put anything into the stack for this one, but we are going to update our I to be the smallest value we've seen so far. So now we come to this 4. We don't have a stack again. So we're going to check, is 4 greater than 1? Yes, it is. So this is a valid ij pair. And we don't have a stack, so this can't be like a k value or anything, right? So we're going to store this. Now we're going to come over here and we're going to check, okay, so we do have a stack, but like I said, if a j value is smaller than this current value, this is redundant, right? So if a j value is smaller than this value, the end of our stack, this can't be a k because k has to be smaller than j, right? K has to be smaller than j. So this can't be a k, but this is redundant because our smallest value can only be better here, and we're going to want to maximize j. So there's no reason to keep this. So essentially what's going to happen here is we're going to pop this, and there's nothing left on our stack now. So now we're going to say, obviously we're going to add this on now, right? So we're going to have 1, 8 now. Then for this value here, we're going to say, okay, is this bigger than the end of our stack? Yes, it is. So this value now is redundant. So we're going to have a 9 here and a 1 here. And now we get to this value. And so is 2 bigger than this j? No, right? So we might have to put it on. We don't really know yet, but now we can check if this is a valid k value, right? So let's check if it's a valid k value. So for it to be a valid k value, we already know that it's smaller than j, because if it was greater than or equal to j, we would have popped this off, right? So in order to check if it's a valid k value, it simply has to be greater than I, and it is greater than I, right? So if it's greater than I, we already know it's less than or smaller than j, then we have a valid answer here. So our answer would be 192 here. And we do have a valid answer. So that's essentially what it's going to look like, is your j values will be strictly decreasing, and then your I values will be decreasing or equal. And let's look at another example. Let's look at maybe a couple more. So we're going to keep the same stack, but let's look at a couple more, just to kind of like understand a little better. So let's say we have that other example of the 30, 60, and then we have like 10, 20, 15, let's say. Something like that. Okay, so let's kind of walk through the same thing. So for the 30, we're going to be at the 31st. We're going to check, is there a stack? No, and we obviously can't put this on. Now remember, our I is going to start at infinity. You could start your I to be the first value in your array, and then just start the second value for your actual loop for the stack. So I is going to be 30 here. Now we are going to go to 60, and we're going to check, is there a stack? No. So is this a valid j? Yes, it's greater than 30. So we're going to put in 60, 30. Okay. Now for this 10, there is a stack. Is this greater than j? No, it's not. Okay, so we're going to check, is it a valid k? So we already know that it's smaller than j, so now it just has to be greater than I, and it's not a greater than I, so this is not a valid k value. And is there a valid ij pair here? No, there's not, because the smallest value is 30, so there is no valid ij pair using this value. But we are going to update I to be this, because this is our new smallest value seen so far. Okay, now we're going to go to this 20, and we're going to check once again, is it greater than j? No, it's not, or equal. If it's equal, we can pop 2 because we don't need duplicate values. So it's not greater than j, but is it a valid ij pair? Yes, it is. So we're going to add it to the stack. So you could see how like this ij can be decreasing because in this example, our I just got better, right? So the I is always going to be better or equal, and this j is always going to be strictly decreasing. And basically, the reason why we don't have to check all the way down is because there's going to be two cases, right, for our new value that we're putting in. So one case is it's greater or equal to the end of the stack, right? So if it's greater than or equal to the end of the stack, like if we're on this 15 or whatever this value is, let's say this value is 100, if it's greater than or equal to the end of the stack, it can't be a k value because it has to be less than j. So then we're going to be popping, right? But if it's smaller than k, what does that kind of represent? Or if it's smaller than j, it's smaller than the end of the stack. So that represents we found the smallest j value that's greater than the value we're currently on. Which means we're optimizing our smallest value to be, because ideally we'd want to use the smallest value as far down as possible because those are going to be the best values, right? The more numbers you've seen, the more likely it is you find the smallest number. So essentially the way this algorithm works is we are literally trying to find the j value that's as small as possible while being bigger than the k, because then we make sure that the I is like, that I has to be, if that I is not less than that k value, then the rest of it can't be either. So we're going to be able to find in O of one time, once we get rid of the redundant j's, is this a valid ijk pair? So finally for this 15, we're going to say, okay, is it less than 20? No, or is it greater than 20? No, it's not, right? So now we're going to check for the k. So in order for it to be a valid k, it has to be greater than 10, and it is. And so this is indeed a valid pair, or a valid ijk where it's 10, 20, 15. Okay. And now let's try to find one more example of one that doesn't work, and then we're going to code it up. Because this definitely, I think it's very good to see a bunch of examples of this, because like this part takes kind of a while to understand, and it's definitely not super intuitive. So definitely like running through a bunch of examples here, this is like one of those stack problems that's not very intuitive at all. But once you realize that you are literally, by making your j's decreasing, we're literally trying to find the first possible j value that's greater than our k, because that will make sure that the I is as small as possible for that j value, so the i's will only be increasing here. So if this I value doesn't work, if this I value is not a match, none of these will work, even though these j values will still be greater than your k. So then that's why you have the O of one lookup. If this one fails, this whole stack would fail. So let's actually go through one last example, and we're going to go through 1, 0, 1, -4, 3. -3. So let's go through this one. Okay. And this one will also kind of show why you can't just store like a local maximum and a local minimum. Because if you did, you'd find some stuff, right? If you store the local minimum or something, you'd be like, oh, look, this was our minimum, this is our maximum, and now we have something that's, you know, greater or less than this value, but it's not greater than this value, so that doesn't work. So that's why you need to store all these things. So let's go through this one. So we don't have an I, like I said, we can just initialize I to be the first element in the list, so we'll make it 1. Now we'll come over here, and we're going to say, is this a valid ij pair? There's nothing in the stack to pop, so we don't need to worry about that. And obviously not, right? Because if this was j, this is smaller than I. So we're going to update our I to be this. Now we're going to come over here, and we're going to check, is this a valid ij pair? And it is, right? We can't have a k yet because there's nothing in our stack. So I would be 0, and this value would be j. So that's fine. Okay, now we'd come over here, and we'd say, okay, is this greater than our j? No, it's not. Is this a valid ij pair? No, it's not, because it's less than 0. So we're going to update 0 to be -4. And then we're going to come over here, and we're going to say, okay, is this greater than our j? No, it's not. So is this also is there a valid ij pair? And while this is the last one, so actually before checking if it's a valid ij pair, you want to check, is it a valid k, right? So to check if it's a valid k, it has to be greater than this value, and it's not. It's smaller than the j, but it's not greater than I. So it's not. And so is this a valid ij pair? And that actually is, right? So I can be -4, and this is this. But then we're done with the array, and we haven't found an answer. So if we never found a valid answer, then we're done. So essentially, we loop through our numbers. We check, is it a valid? Is it greater than the j values currently? If it is, we pop those, and then we check. It's either a valid ij pair or it's the new smallest number, right? One or the other. And also, we also have to check before doing that, if there is a stack still, we have to check, is it a valid k? And then if we go through all our numbers and we didn't find anything, then we're fine. And this is going to be O of n time and O of n space, because essentially, worst case, you're only pushing the numbers once on the stack and popping once. And you're going to have O1 lookups for, is it a valid k? So now we can code it up. So I'm just going to make small the smallest number. It's actually... We'll make that -infinity, or actually we want to make it infinity, right? So we're going to make that infinity, and now we're going to loop through every number, and we also need a stack. So we're going to loop through every number for num and nums. So first we're going to pop j values that are smaller than the current j value we're on, because that's redundant information. So we can say while stack and stack, and I'm actually going to store them in terms of the j is going to come before the I. So it's going to be stack -1, 0, it's going to be j and then I in the stack. So if this is smaller than or equal to the number, and the reason why we're going to get rid of the equal to as well, because we're going to add this onto the stack, so we don't need like duplicate numbers. There's no point. Also, if they are equal, actually you still want the new number because the smallest index might have gotten updated. So you want to get rid of it anyway. Okay, so if this is the case, then we're going to pop. So now that we do that, we have to check, is it a valid k? So we already know that it's less than the end of the stack. We already know it's less than the end of the j value, but now we have to check, is it greater than the I value? And the stack actually has to exist as well. So if stack and number is greater than stack -1, 1, which remember we're storing them in terms of j and then I. So if this is the case, then we have a valid solution, so we could return true. Now we have to check, is it either it either has to be a valid ij pair, or it's going to be our new small number, or it equals a small number, essentially, which is fine, right? So we can say if number is greater than small, then that's going to be a valid ij pair, right? So if number is greater than small, then we can just add that to the stack. So stack.append. And we're going to put number and this small number. And then finally, we are going to update our small number to be the minimum of the old small number and the number. So And obviously, if the number is greater here, then we don't have to do that, right? Because that'll never be the case. So else, we can actually even make it, we can even just make it, we don't even need to do a minimum, I think. We can just have small b the number, because they're either going to be equal or the new number is going to be smaller. So we can just say this. We don't have to like check for a maximum or minimum or anything. And this should theoretically work. Now we just return false if we never find anything. So let's see what happens. Okay. Okay, so you can see it's quite efficient. And so once again, to go through the time and space complexity here. So, and this like I said, this is one of the stack ones that's kind of really hard to figure out, like, why is it actually working? And once you realize that, like, you want for any of the minimums that fails, like if your minimum doesn't satisfy the condition, then every minimum to the left of it will also not satisfy the condition, because the minimums only get better, like I showed in the picture. Once you understand that, then you kind of understand the problem. So for the time, it's going to be O of n, because essentially we're looping through our nums, and we are either putting the number on the stack once or not, and we're removing it from the stack once or not, right? So worst case scenario, you put every number on the stack, and then you remove from the stack. So that's still O of n. And yeah, and then for the space, we do have the stack, so you might have like every number from the, you might actually put every number on the stack. That's possible. Because, like, let's say it's literally just like this, an increasing array, then you would put every single number on, because every new index... well, actually, I guess what would happen here is you would never have them all in the same time. So actually, I think you want this to be, like, decreasing probably to have every number on. I'm not exactly sure how you'd have every number on, but either way, it's going to be O n, because you can't have multiple numbers on here. I think maybe decreasing it would. I would have to double check, but yeah, this is going to be O n because we do have a stack. So yeah, I think that's going to be all for this video. So hopefully you enjoy it. Definitely quite a difficult medium problem, I would say. And like, even once you see the solution, it might not be super clear still. So I definitely encourage you to like walk through the examples and see why this works. And yeah, if you did like this video, please like it and subscribe to the channel. And I'll see you in the next one. Thanks for watching.